Okay, so remember I said when we were talking about 5.3 that this section will be about a lot of the properties of logarithms. So in 5.5, which we're going to go over next week, so that will be extended for you guys, we're going to learn how to solve logarithmic and exponential equations. So like solve them, get the variable x by itself. And so we need to know some of these properties in order to do that. So what these properties here are useful for is to rewrite a logarithmic function in a different kind of form. So we already learned how to write it in exponential form, but now these are different properties to write it in. Well, they'll still be logarithmics, but it's separating them into a sum or difference or product of logs. So let's go over it. So the first one is the product rule for logarithms. So that says that for any positive numbers m and n, if I have, and any logarithmic base a, if I have log base a of m times n inside my log function, that this can be separated into a sum of two separate log expressions, where the first one has the first factor in the product, m, and the second one has the second factor in the product, n. So this would be equal to log base a of m plus log base a of n. So an example, if I had log base 3 of 2x, and I'll put this in parentheses just to show you that that is inside the log function. This is going to be equal to log base 3 of 2 plus log base 3 of x. Because the 2x, that's being multiplied by each other. And so I can use that property and rewrite it as a sum of their two logs. And then I just keep whatever base originally was there in both of my log expressions. Whatever base was there. Okay? And we're going to do a bunch of these examples, so hopefully if we don't run out of time. So the next one is called the quotient rule of logarithms. So kind of similar, but this one's separated into a difference of two logs if you have a quotient inside of your log function. So if I have log base a of m divided by n, then this is separated into the difference of log base a of the numerator, which is m, minus log base a of the denominator, which is n. So one way I kind of remember this, even though you can have a formula, is that the expression on the left has like a fraction bar, and this has like, a subtraction bar. But you always have to take what's on top, which is the m. That one needs to go first in the first expression. The order matters there. So it's always log base a of the numerator minus log base a of the denominator. And so I also always remembered these very similar to like the exponent rules. Like if something's being multiplied, well, usually it's bigger, so that's addition. If something's being divided, that usually gets smaller, so that's subtraction. It's very similar to those exponent rules, dividing like bases or multiplying like bases. Anyway, so an example here, if I had log base x of 4 over y, this would be equal to log base x of 4 minus log base x of y. Was my numerator, and the y was my denominator, and then I kept the base x. And then the last one is called the power rule of logarithms. So this one says that if, and this p here is supposed to be an n, forgot to change it, for any positive m and any logarithmic base and any real number n, if I have an exponent inside my log function, so this is log base a of m to the n power, then I can just pull that exponent out and put it out front, and it becomes multiplied by what's left. So this is equal to n times the log base a of m. So I just always thought of that as like I need to pull that exponent out and just bring it in the front and multiply by what's left. So an example, if I had log base 5 of x squared, this would be equal to 2 times log base 5 of x. So I just take that exponent of 2 and bring it out front. Okay. So eventually in this section and in your homework, they're going to give you problems where you will have to rewrite something using all of these rules. Like all of them will be combined into one problem. So we're going to do that. But before we do that, I just have a couple of simple ones here just to kind of, make sure we understand what we're doing. And you'll have some of these simpler ones in your homework. So this says number 1, and number 1's even kind of telling us exactly what to do, but it's saying to express the following logarithm as a difference of logarithms, because there's a quotient here, so this would be rule 2. I'm going to label these using rule 2, or the quotient rule. And it says simplify if possible. So I'm going to talk about what that means. Okay, so this will become, if I use that rule, I'll keep the log base 4. The 64 will go in the first log, because that's my numerator. And then this would be minus, because they're being divided, log base 4 of 16, which is the denominator. Okay, so that's using the quotient rule. And then for these, because it tells me to simplify, and these are all numbers, there's no variables, I can use what I learned about logs. So for the first one, this is asking me what do I need to raise 4 to, or what exponent do I need to raise 4 to in order for it to equal 64? And that would be 3. 4 cubed is equal to 64. So that whole thing will just become 3. And then what do I need to raise 4 to in order to get it to equal 16? 2. So this will become 4 minus 2. Bring down that minus sign as well. Or did I say 4 minus 2? 3 minus 2. And that's just equal to 1. So this whole thing was just equal to 1.
This is where you would say y equals 1.
Well,
Not really.
you wouldn't, no, you don't. Well, you would just, this is equal to 1, the log expression. So like you wouldn't ever, well, none of these you would ever enter in like an equation for an answer, y equals 1. You wouldn't do that. You just enter in the answer. Now, without using the quotient rule, I could have also just simplified. 64 divided by 16 is 4. So this is the same thing as log base 4 of 4, which is also just equal to 1.
Oh.
Yeah, 64 divided by 16 is 4. But I just was wanting to show you how to do this because they won't all work out that way, obviously. So you will have to separate them. But you could have simplified that fraction first and then did it that way. Okay? All right. Number 2 says express the following as a product of logarithms and simplify if possible. Excuse me. So this one is log base 5 of 25 cubed. So this is using that third rule up here, the power rule, because there's an exponent in there. So this would be equal to 3 times log base 5 of 25. Because I just take that exponent of 3 and I bring it out front. And it gets multiplied by what's left. And then I'm going to keep simplifying because, again, these are all just numbers. So what do I need to raise 5 to for it to equal 25? 2. So this will become 3 times 2, which is just 6. So of course, these that are all numbers, you could just plug into your calculator too. But when it starts being all letters, like this one, you can't. So you will have to know how to use these rules still. Okay? All right, so 3. We're getting a little bit trickier here now. 3 says to express the following logarithm as a sum and difference of logarithms and simplify as much as possible. Now, this is how they will say it in Pearson. This will be your instructions. And when it says to simplify as much as possible, it means that you need to expand this as much as possible until there's no more of these rules that you can use. So you're looking to see if there's a product in there in your log, you're looking to see if there's a quotient, and you're looking to see if there's an exponent. So when it's all like variables, mostly all, or just if there's a variable at all present, you want to simplify this until you can't use any of these rules anymore. Okay? And in this problem, there's going to be multiple rules. Actually, we're going to use all 3 of them. Now, the order in which you want to do this, notice that this is just one log expression, right? So when it says to express as a sum and difference of logs, we're like expanding it. We're going to write it into multiple logs. So the order in which you want to do this is you want to use the quotient rule first and separate it into a difference, and then use the product rule, if there is any, if it's possible, and then look for the power rule. So this is the order in which you will do these when you're expanding. So I see a fraction for sure. So I'm definitely going to use the quotient rule first. So step 1, I will just rewrite the problem here. So step 1, I'm going to separate this into a difference. So this would be log base b of the numerator, which is s times t, minus log base b of the denominator, which is p cubed. I should probably move this down a little bit. So that was step 1, using the quotient rule. Now step 2, I will look for the product rule. Is there anything being multiplied inside of my logs? Well, here there is, because that's s times t in that log. So that can now be separated into a sum of 2 logs. Well, let me write what I'm doing. This is the quotient rule. Okay, step 2. So I'm going to separate that first term here using the product rule. So that would be log base b of s plus log base b of t, and then bring down the minus log base b of p cubed. I could have already taken care of the product rule in that step, but I'm just doing one step at a time. So now I just use the power rule there. So now there's nothing else being multiplied inside my logs. There's nothing else being divided. The only other thing I need to do is the power rule, because I do have an exponent. So step 3 will become log base b of s plus log base b of t. That's not changing. But the last term here will become minus 3 times log base b of p, because I pulled that exponent out front. So that was using the power rule. This is the order I did it in. Okay, so now I have nothing left I can do. There's nothing being multiplied in my logs, there's nothing being divided, and there's no more exponents. So this is my final answer. So that's what they mean when they say simplify. You need to keep going till you don't have anything else to do. Good so far? Okay. All right. So some of them will have these radicals in them. And again, remember I said that rule for radicals was really important in this section, because if I have a radical in one of these log expressions and they're asking me to expand it into a sum or difference, you need to remember that a radical creates a fraction exponent. So that would be included in the power rule. So this is that rule again. But still, I'm going to still go in the same order. Quotient rule first. And then if I have a product rule, I would do that second. And then I would do the power rule last. And if there isn't one of these, you just skip it. Okay, so step 1. I have things being divided in here, so that's my quotient rule. So that would become log base 3 of the cube root of x, because that's my numerator, minus log base 3 of y, because that's my denominator. So that's using the quotient rule. Okay, so now I don't have anything being multiplied by each other inside of my logs. So I don't need to use the product rule. But I do need to rewrite that radical as its exponent. So this would be log base 3. What's the cube root of x in terms of an exponent? 1/3. So that would become x to the 1/3 power. And just to show you a couple more examples, so the cube root of x is x to the 1/3. The fourth root of y is y to the 1/4. If I had the third root of x squared, this would be x to the 2/3 power, because now there's an exponent of 2 in there. Just a couple examples of using this rule. We need to get real comfortable with that. Okay, bring down the other one, log base 3 of y. So that was just really rewriting it. That's not one of my rules I've used yet. But now that I've rewritten it as an exponent, I can use the power rule and pull that exponent of 1/3 out front. So it'd become 1/3 times log base 3 of x minus log base 3 of y. So here I used the power rule. And that's it. I don't have anything else I can do. Nothing being multiplied in my logs, nothing being divided, and no exponents. Okay? All right, number 5. Number 5 is, a little trickier. And there's actually 3 different ways you can do number 5. A lot of times in math, there's different paths to get to the same answer. I'm going to stick with what I think is the easiest path. And that is to separate this radical into a product of 2 radicals. Remember when we learned that rule, the square root of a times b is equal to the square root of a times the square root of b? So that's what I'm going to use, and that is the property we should be most familiar with, other than the other properties I'm thinking about to proceed in the other paths. So this is what I'm going to stick with. So this is equal to log base c of the square root of x times the square root of y to the 4th power. And so now I have a product. in there, a product of two things inside of my log. There's nothing being divided, there's no fraction, so I'm skipping the quotient rule. But this is a product of two things, so I need to use the product rule. I'm going to write these out again, though, just to remind you of the order in which we want to do things. I get to skip the quotient rule, so now I'm going to do the product rule. So this would be equal to log base c of the square root of x plus log base c of the square root of y to the fourth. And then I want to rewrite these radicals as their fraction exponents. So the square root of x would be what?
1/2.
1/2. Log base c of x to the 1/2 power. Now the other one, you can get to the answer in two different ways. I'm going to write these over here. So everyone thinks differently. So I'm going to write this little note over here. The square root of y to the fourth. Well, technically there's a 2 here for the square root. So just directly using that formula up there, this would be equal to y to the 4 over 2 power. Right? And 4 over 2 is just equal to 2. 4 divided by 2 is 2. So this is equal to y squared. Or you can think of it as this is the square root of y to the fourth. So, well, all of that would just be raised to the 1/2 power, the y to the fourth. But now this is a power to a power, so you need to multiply those. And 4 times 1/2 is 2. 1/2 of 4 is 2. So this is... So either way, if you want to use directly use the formula, I mean, you're kind of using the formula in both cases, but yeah. I don't know where your brain went to think about that, so I just wanted to include both options. But either way, this just becomes y squared. And I'm going to include that there so everyone can know where I got that from. Okay, so that's just rewriting them as their fraction exponent equivalents, even though that one didn't turn out to be a fraction because it's simplified nicely. And now we can use the power rule and pull out those exponents and multiply by what's left. So that would be 1/2 times log base c of x plus 2 times log base c of y. And that's it. I can't do anything else. That would be my final answer. All right, number 6. All right, we good? Number 6. Sorry. Same thing. Okay, so we're going to do the quotient rule first. And then we're going to look for anything that could be using the product rule. And then we're going to look for the power rule. All right. So I definitely have a quotient in here because there's a fraction bar. So that will be separated into subtraction. So that would become log base A of w squared times y cubed, because that's everything in the numerator, minus log base A of b times c squared. So that's using the quotient rule. And now I will look for anything being multiplied inside the logs, which I definitely have in both of those. So I need to use the product rule next and separate both of those into sums. Okay, so the first one would be log base A of w squared plus log base A of y cubed, because that's what's being multiplied here, w squared times y cubed. So all of that, I just used the product rule on the first term. Okay, the second term is a little tricky because of that minus sign. So if I'm going to separate this expression here, log base A of b times c squared, into a sum of two things, then I need to put it all in parentheses because I was originally subtracting that term. So if that term becomes more terms, I need to be subtracting all of those terms because that's what it equals, right? Make sense? So anytime that you have to use the product rule to separate into addition and there's a minus in front of that log, or in front of that term, that's a term, you need to put it in parentheses. So this would become, in my parentheses, would become log base A of b plus log base A of c squared. And then I will eventually have to distribute that negative to both of those terms. There's always one, right? Oh, wait, what am I doing? I'm using the product rule here. I don't know why I stopped labeling my steps, but all right. And so now I can use the power rule and bring those exponents out front. So this will become 2 times log base A of w plus 3 times log base A of y. I'm going to keep this in parentheses for right now. So minus log base A of b, because there was no exponent there, plus 2 times log base A of c. So all of those, I used the power rule. Now, if I'm being honest with you, I think Pearson would accept this answer without you distributing it as long as you had the parentheses. But it's definitely a good habit to get into simplifying all the way. I don't know if they would or not, to be honest. I think they would, but I don't remember. But if I distributed the negative, this would be 2 log base a of w plus 3 log base a of y minus log base a of b minus 2 log base a of c. But I definitely want to distribute it here for the purpose of what I'm about to say. So that would be my final answer. I'm trying to bring it up for you guys. I know it gets blurry when I do that.
That's so crazy.
They're fun.
Yeah.
It's like a little puzzle. You just gotta think of it as like a little game, a little puzzle game. Challenge. Life is nothing but a challenge. Okay, so what I want to say here, what's important? What we're about to do on the next page is we're going to start going backwards. Okay, so they're going to give you problems like this, and then they want you to go backwards and express it into one single log, like this. They want you to go back to that. So I want to give you a trick right here, and notice that anytime you see, when we start going backwards, if you see a, oh my gosh, I need to stop doing that. If you see a minus in front of a term, that means that both of those terms need to end up in the denominator of the fraction. You see how this one has a b in its log and this one has the c, and then that 2 was the exponent for that. And that's what was in this denominator, right? B and c squared. So when we start going backwards, if there is a minus sign in front of the term, that means those need to be in your denominator of your final answer. Okay, but anyways, so let's do an example. Okay, it's not that bad. Okay, so when you go backwards, you kind of do these steps backwards. So now we're going to do the power rule first, then the product rule, and then the quotient rule last. Y'all are funny. Okay. So this is our problem. They want me to express it as a single log. So for the power rule, I'm looking for things that are being multiplied in front of the log. So this has a 5 in front of it, and this one has a 1/4 in front of it, right? So let me just write that rule for you backwards. If it's n times log base a of m, this is equal to log base a of m to the nth power. So now I'm just putting that back up as its exponent. So this 5 will become the exponent of that x. And this 1/4 will become the exponent of that z. So this will become log base b of x to the 5th power minus log base b of y, because I didn't do anything with that. There's no constant in front of it besides the negative, but that's not what I'm looking for. Plus log base b of z to the 1/4 power. Okay, so I just used the power rule. So now and I'll highlight these too. I'm looking for anything that would be the product rule. So the product rule going backwards would be if it's a sum of two logs, log base a of m plus log base a of n, then this would be combined to log base a of m times n, going backwards. So here you're looking for anything that that's positive. Any of those terms that are positive. Yep. You have a question? Oh. So this whole term is positive because of the plus sign in front of it. And this whole term is positive because there's no sign in front of it, so it's positive. So those are the two I'm going to combine together using the product rule. So that would become log base b of x to the 5th power times z to the 1/4 power. Because I'm just taking what's in those two logs and multiplying it together and then keeping the log base b. And then I'll bring down my minus log base b of y. And I just use the product rule. And then finally, I will combine both of these using the quotient rule. So going backwards, this would be log base a of m minus log base a of n. So if two things are being subtracted, then this becomes log base a of m divided by n. It's the quotient rule. Oops. So that's what's happening here. I have log base b of x to the 5th times x to the 1/4 minus log base b of y. So I would combine this into one single log, just always keeping my log base b. What came first, which is the x to the 5th power times z to the 1/4 power goes on top. And then that goes over y, because that's what's in that second log. And so I just used the quotient rule.
Are we worried about making Z a radical?
No. You don't have to. You don't have to. They'll accept that. This answer. Good question. I was about to say that. So yeah, that would be the final answer. Of course, it could be written as the fourth root of z if you wanted to, and you'd still get it right. So I know it's harder to go that way.
This is so crazy.
Dang, I wasted more time in this class and I still got further than my other ones.
Because we're better.
I'm just kidding.
Alright.
I'm joking. Just joking. Okay, so that would be my final answer. Probably should have done more examples of that, but I didn't because I knew I was going to be running out of time. All right, so there's only a couple more things. Let's just go over this. You'll see this in your homework. Number 8, so it says, given that log base A of 2 is equal to 0.431 and log base A of 3 is equal to this decimal, find each of the following if possible. So when they give you problems like that, you're trying to rewrite this using the properties we've just learned so that you can use these decimal equivalents. Because if I can separate anything into log base A of 2, then I know it's equal to this. And same thing with log base A of 3. So for the first one, 6 can be separated into 3 times 2, which would use these two numbers, 2 and 3 here. So that's what I want to do. I want to rewrite this as log base A of 3 times 2 and then separate it into a sum because that's the product rule. So this would be log base A of 3 plus log base A of 2. And then I can replace these with what they're equal to. So they told me log base A of 3 is equal to this, which is 0.683. Plus, and log base 2 is equal to 0.431. So in my calculator, that would equal 1.114. So that's what you're trying to do with these. You're just trying to use your properties and rewrite it so you can get these separate on their own and use their decimal equivalents. So this one used the product rule. The next one, this one's pretty obvious. We're just going to use the quotient rule because it's already in a fraction for us. So this would be log base A of 2 minus log base A of 3. And then we know what these equal. Log base A of 2 is equal to 0.431. And log base A of 3 is equal to 0.683. And that is equal to negative 0.252. And then the last one is log base A of 81. So this one's a little harder to see. There's definitely no way I could separate that into a product with 2 or 3 to get it to equal 81. There's nothing I can do with division. So the only thing left is using the power rule. I want to try and write this as a power of 3 or 2. And I can actually write it as a power of 3. Because we know that 9 times 9 is 81, right? And 9 is 3 squared. So this would actually be 3 to the 4th. So these are harder because you can't just plug these in your calculator. You kind of have to think about them. But this is equal to log base A of 3 to the 4th power. And now I can use that power rule and pull that 4 out front. So this would become 4 times log base A of 3. And I know that log base A of 3 is equal to that 0.683, because that's what they told me. So plugging that into my calculator will give me 4 times 0.683 would be equal to 2.732. I'm going to continue with these last two just for the video, but you guys are free to go if you want to go. Alright, so these are just the last two properties of this section. So this one is called the logarithm of a base to a power. And so this says that if I have log base A of a to the x power, this is just equal to x. Well, that's because log base A of a to the x, I can rewrite this using that power rule and bring that x out front, because that's my exponent. So that'll be x times log base A of a. And then because these match here, I know that this is just equal to 1. Log base A of a is just equal to 1. So this becomes x times 1, which is just x. So that's why this rule is the way it is. So just a couple examples of that. If I had log base 3 of 3 squared, this would just be equal to 2. If I had log base 5 of 5 to the power of y, this would just be equal to y. So it's almost like when those match, they just cancel each other and leaves you with the exponent. If I had log base 1/2 of 1/2 raised to the power of 6, this would just be equal to 6. And then the last one, and I'll be done, is a base to a logarithmic power. So this says if I have a being raised to the exponent of log base A of x, then this is just equal to x. So if this base of the exponent and this base of the log match, again, they kind of just cancel and it just leaves me with what's left, which is the x. I'm not going to prove this one to you because it takes a little bit more knowledge of what we're going to learn next week of solving these equations. But I'll just give you a couple examples. So if I have 3 raised to the log base 3 of 5, this would just be equal to 5 because this base, this exponent matches the base of that log. If I had e to the ln of x power, this would just be equal to x, because technically ln is log base e. So this is very useful, especially if you go to higher maths. You'll be using that to solve equations a lot. So anytime you have e raised to the ln of x, it's kind of like they just cancel each other and it's just equal to x. Okay, that's it. Okay.